Hey, welcome to The Explainer. Today, we're going to put on our detective hats because we are going to crack a secret code. A code that controls one of the most important things in all of chemistry and industry, just how fast a reaction happens. So, let's just dive right in. Picture this. You're in charge of some huge chemical factory. You need to make your product, and you want to do it fast, for efficiency. But maybe not so fast that things get dangerous or crazy expensive. So how do you get it just right? How do you actually control the speed? That's the big puzzle we're going to solve. Now, your first instinct might be to look at the chemical equation, right? The basic recipe. But here's the thing. That's a total red herring. It tells you what ingredients you need and what you'll end up with. But it tells you absolutely zero about how fast you'll get there. For that, we need to look somewhere else entirely. And that brings us to our very first clue. The key to all of this, the secret to controlling reaction speed. It isn't in that main recipe. It's hidden in a secret formula that chemists have to figure out for every single reaction they study. And that secret formula? It's called the rate law. This is the whole shebang. It's a simple little equation that creates a direct link between how much stuff you put in, your reactants, and the actual speed of the reaction. This is the code we're here to crack. So, this is what that code looks like. Rate, that's our speed. The brackets, A and B, that's just the concentration of our ingredients. But the real secrets, the parts that hold all the power, are these other values, K, M, and N. K is what we call the rate constant, kind of like a unique fingerprint for every reaction. And M and N, those are the orders. And here's the kicker. You can't just look these up. You have to discover them through experiment.
Okay, so if you have to discover the code through experiments, how in the world do chemists actually do that? Well, turns out they use this really clever systematic process. It's just like a detective interviewing suspects one at a time.
This process is called the method of initial rates, and it's brilliant in its simplicity. First, you just run the reaction and clock its speed right at the beginning. Then, you do it all over again, but you change the amount of only one of your ingredients. Just one. Everything else stays exactly the same. Then you just compare the new speed to the old one. By isolating each ingredient like that, you can see exactly how much of a difference it makes. All right, enough theory. It's time to put on our detective hats for real and look at some actual data. We're going to use this exact method to decode the rate law for a real chemical reaction. Here it is. This is our clue board. We're looking at a reaction between nitric oxide and hydrogen. In this table, it's just showing us the results from 3 different experiments. We tweaked the amounts we started with and measured the speed each time. Our secret numbers, M and N, they're hiding right here in this data. Let's find them. Okay, first suspect up, hydrogen. Let's compare run 1 and run 2. See how the nitric oxide concentration stays exactly the same? But we doubled the amount of hydrogen. Now, look at the result. What happened to the rate? It doubled too. It's a perfect match. So, because doubling the concentration led to a doubling of the rate, we say the reaction is first order for hydrogen. We've found our first secret number. For hydrogen, that little exponent N is just 1. One suspect down, 1 to go. Now for our second suspect, nitric oxide. Let's look at runs 2 and 3. This time, the hydrogen is held constant, but we doubled the nitric oxide. And, whoa, look at the rate. It doesn't just double. It goes up by a factor of 4. It quadruples. Now this is interesting. That huge jump is our biggest clue. When you double the concentration of something and the rate quadruples, that tells you the relationship is squared. So the reaction is second order with respect to nitric oxide. And just like that, we found our second secret number. M is 2. And boom, the code is cracked. We just put our findings together to write out the full rate law. The speed of this thing is equal to our constant K times the concentration of nitric oxide squared times the concentration of hydrogen to the power of 1. We now have the exact precise formula to control this reaction.
So we found these numbers. We call them orders. First order, second order. What does that actually give us? Well, it gives us the power of precise control. And understanding what these orders mean is everything.
Let's start with what we call a zero-order reactant.
For a substance like this, you could double it, triple it, dump a bucketful in, it doesn't matter. The reaction speed does not change one bit. The rate is totally independent of this guy. He's just along for the ride.
Then you have first order, which is what we saw with our hydrogen. This is a nice, clean, proportional relationship. You double the concentration, you double the rate. You triple it, you triple the rate. It's a really predictable lever of control.
And finally, you get to second order, like our nitric oxide. This is the real powerhouse. The effect here is squared. So doubling the concentration gets you times 4 times the speed. If you tripled it, you'd get 9 times the speed. This gives chemists an incredibly powerful dial to turn to make huge changes in reaction speed.
So, what are the big takeaways from our little investigation? First and most important, forget the balanced equation for speed. You can only find it by doing the experiment. Second, the rate law is that secret code that connects how much stuff you have to how fast it goes. Third, the order of each ingredient tells you exactly how much influence it has, whether it's a lot, a little, or none at all. And finally, remember this isn't just for a textbook. This is the knowledge that lets us fine-tune everything from making new drugs to creating materials.
I mean, this whole idea of control is just so powerful. And it really makes you think, now that you know the code, what real-world process would you want to tweak? Would you want to speed up how fast plastic breaks down in the ocean? Or maybe slow down how fast fruit ripens so it doesn't spoil? The possibilities are pretty mind-blowing. Thanks for watching.